Hello there, and welcome back to the sleepy ocean. Tonight, we are going to let the current take us, surrendering all effort to the most powerful river in the world. But this is not a river of fresh water flowing over rocks and through valleys. It is a river of salt, a massive indigo highway that flows through the ocean itself. We are drifting into the Gulf Stream. To understand this phenomenon, we must first visualize the Atlantic Ocean not as a static bowl of water, but as a living, breathing engine of circulation. The Gulf Stream is the western limb of the North Atlantic Gyre, a colossal swirl of water that rotates clockwise between the continents. It is a distinct ribbon of blue warmth cutting through the colder green waters of the Atlantic, a boundary line that is visible from space. It is so distinct that in the 19th century, the oceanographer Matthew Fontaine Maury described it as a river in the ocean that never overflows its banks and whose bottom and sides are made of cold water. It carries more water than all the terrestrial rivers of Earth combined, moving with a silent, relentless power that has shaped the climate, the history, and the biology of the planet for millions of years. The origins of this massive current begin far to the south, in the tropical heat of the Caribbean Sea and the Gulf of Mexico. Here, the trade winds, blowing steadily from east to west across the equatorial Atlantic, pile up water against the coast of Central America. The sea level in the Caribbean is actually measurably higher than it is on the Atlantic coast of the United States, creating a hydrostatic pressure gradient. This piled-up water needs a release valve. It squeezes through the narrow Yucatan Channel and loops deep into the Gulf of Mexico, forming what is known as the loop current. This loop is the warm, beating heart of the system. It swirls in the Gulf, gathering heat from the tropical sun, becoming supercharged with thermal energy. Eventually, the pressure becomes too great, and the water is forced to exit through the only available door, the Straits of Florida. This narrow passage between the tip of Florida and the islands of Cuba and the Bahamas acts as a high-pressure nozzle. The water accelerates as it is pushed through this gap, transforming from a drifting mass into a high-velocity jet, launching the Gulf Stream on its journey northward with the force of a fire hose aimed at the pole. The sheer volume of water moving through the Florida Straits is difficult to comprehend without a specialized unit of measurement known as the spheredrup. One spheredrup equals 1 million cubic meters of water per second. The flow of all the fresh water in the Amazon River, the largest river on land, is roughly 1/5 of a spheredrup. The Gulf Stream, as it exits Florida, flows at a rate of about 30 spheredrups. By the time it reaches the open ocean off the coast of Newfoundland, having picked up additional water through recirculation, its flow can increase to 150 spheredrups. This means that the Gulf Stream is moving more water every single second than all the rain, snow, and river runoff falling on the entire planet combined. It is a liquid avalanche that never stops, a constant, silent thunder of water moving north, carrying the weight of the ocean on its back without making a sound that can be heard above the waves. The color of the Gulf Stream is a defining feature that has mesmerized sailors for centuries, a deep, piercing indigo that contrasts sharply with the surrounding sea. This color is not an illusion. It is a statement of biological emptiness. The water of the Gulf Stream originates in the nutrient-poor tropics, where the warm surface water prevents the upwelling of cold, mineral-rich water from the deep. Without nutrients, there is very little phytoplankton, the microscopic plants that turn water green or brown. Because the water is so pure and free of particulate matter, the sunlight penetrates deep into the column, and the water molecules absorb the red end of the spectrum, scattering only the deepest, purest blue back to the eye. Pilots flying over the Atlantic can often see a physical line in the ocean where the murky, green, nutrient-rich water of the continental shelf meets the clear, ink-blue water of the stream. It is a wall of color, a visual border where two different worlds touch but do not mix. Embedded within this blue water is an immense amount of thermal energy, making the Gulf Stream the central heating system for the Northern Hemisphere. As the water travels through the tropics, it absorbs solar radiation, heating up to temperatures of over 80 degrees Fahrenheit. It holds this heat with incredible efficiency as it travels north. The specific heat capacity of water is very high, meaning it takes a long time to cool down. As the stream moves past the Carolinas and heads toward Europe, it slowly releases this stored heat into the atmosphere. The amount of heat released by the Gulf Stream is staggering. It is estimated to be equal to 100 times the world's total energy demand. This heat transfer is why palm trees can grow on the Scilly Isles off the coast of England, and why the ports of Norway remain ice-free in the winter, while ports at the same latitude in Canada freeze solid. The stream is a chimney, breathing the warmth of the Caribbean into the cold, grey skies of the North Atlantic. The discovery of the Gulf Stream by Europeans is credited to the Spanish conquistador Juan Ponce de Leon in 1513, though indigenous peoples had undoubtedly known of it for millennia. While searching for the Fountain of Youth in Florida, Ponce de Leon's ships encountered a force they could not explain. They were sailing south, and they had a strong wind behind them, pushing them forward. Yet, the ships were moving backward. The current was so strong that it overpowered the wind in the sails. The sailors were terrified, believing they were being gripped by a sea monster or a supernatural force. They had stumbled into the axis of the stream, the fastest part of the river. This discovery changed the world. The Spanish realized that while the trip to the Americas required the southern trade winds, the trip back to Spain could be made effortlessly by riding this river north and east. It became the superhighway of the Spanish treasure fleets, a conveyor belt of gold and silver that powered the empires of Europe. Centuries later, the first scientific map of the Gulf Stream was created by Benjamin Franklin, who was serving as the Deputy Postmaster General for the American colonies. Franklin noticed a peculiar inefficiency in the mail system. The mail ships sailing from England to America took 2 weeks longer than the American whaling ships making the same journey. He consulted his cousin, a Nantucket whaler named Timothy Folger. Folger explained that the British captains were sailing against a current that the whalers knew to avoid. The whalers tracked the whales, which stayed on the edges of the current to feed, so they knew exactly where the river ran. Franklin asked Folger to sketch the current on a chart. He then began taking temperature readings of the ocean during his own voyages, realizing that a simple thermometer could tell a sailor if he was in the stream. By measuring the warmth of the water, a captain could find the fast lane or avoid the headwind. Franklin published his chart in 1770, revealing the invisible river to the world of commerce and science. The western edge of the Gulf Stream, particularly off the coast of the United States, is known as the Wall. This is not a solid wall, but a steep gradient of temperature and speed. In the span of just a few miles, the water temperature can jump from 50 degrees to 75 degrees. This sharp boundary creates a physical barrier for marine life and sound. The current here is fastest, sometimes reaching speeds of 5 or 6 miles per hour. It is a place of violent shear, where the stagnant slope water rubs against the racing tropical water. This friction creates visible surface phenomena, lines of foam, changes in wave patterns, and even a difference in sea level. Ships entering the Wall can feel a physical lurch as the bow hits the fast water, and the humidity in the air changes instantly as the warm vapor rising from the stream hits the cool coastal breeze. The surface of the ocean within the Gulf Stream is not level with the rest of the Atlantic. It is actually a tilted hill of water. Due to the rotation of the Earth and the Coriolis effect, The water in the center of the North Atlantic gyre, the Sargasso Sea, is pushed inward and piled up. The Gulf Stream flows along the western flank of this hill. The sea level in the stream can be several feet higher than the water on the continental shelf. This slope is maintained by a geostrophic balance, a tug-of-war between gravity trying to pull the water down the hill and the Coriolis force trying to push it to the right. The result is a current that flows parallel to the slope, essentially running along the side of a liquid mountain that spans the entire ocean basin. This tilt is invisible to the naked eye, but is a fundamental reality of ocean physics. Ships sailing into the Sargasso are sailing uphill. For the loggerhead sea turtles that hatch on the beaches of Florida and Georgia, the Gulf Stream is a lifeline that carries them through their lost years. When the hatchlings scramble into the surf, they swim frantically offshore until they hit the current. Once they enter the stream, they stop swimming. They become passengers. They climb onto floating mats of sargassum weed and let the river carry them north and east. The stream transports them away from the predator-filled coastal waters and into the relative safety of the open Atlantic. They will ride this conveyor belt for years, drifting toward the Azores and Europe before circling back as adults. Without the Gulf Stream, these tiny turtles would be stranded in the cold waters of the shelf and would likely perish. The current is their nursery, a moving cradle that rocks them gently across thousands of miles of danger. The floating forests of sargassum weed that the turtles rely on are a unique feature of the Gulf Stream system. This brown algae is holopelagic, meaning it spends its entire life floating, never attaching to the seafloor. It is kept afloat by millions of tiny, gas-filled berries that look like grapes. The Gulf Stream acts as a broom, sweeping this weed up from the Gulf of Mexico and the Caribbean and organizing it into long, golden lines known as windrows. These lines can stretch for miles, visible from the deck of a ship, as yellow stripes on the blue water. Eventually, the stream sheds this weed into the calm center of the gyre, creating the Sargasso Sea. But while it is in the current, the sargassum is a mobile ecosystem, a raft of life teeming with specialized crabs, shrimp, and fish that have evolved to look exactly like the weed, drifting north in a camouflage of gold and brown. As the Gulf Stream leaves the coast of Cape Hatteras and heads into the deep ocean, it begins to meander like a garden hose left running on a lawn. These meanders are massive, snake-like curves that can extend for hundreds of miles. The stream becomes unstable as it leaves the guiding wall of the continental shelf. These loops grow larger and larger until they pinch off entirely, creating independent, swirling islands of water known as eddies or rings. This process is the oceanic equivalent of a river forming an oxbow lake, but on a gigantic, rotating scale. The formation of a ring is a cataclysmic event for the plankton and fish trapped inside. They are suddenly cut off from their parent river and set adrift in a hostile, foreign body of water, spinning slowly in the dark. When a meander pinches off to the north of the Gulf Stream, it captures a core of warm, Sargasso seawater and traps it in the cold slope water. This is called a warm core ring. These rings spin clockwise and can be 100 miles wide. They are tropical oases wandering through a cold desert. Inside the ring, tropical fish, coral larvae, and warm water plankton continue to live, surviving on the heat stored in the core. These rings can persist for months or even a year, slowly cooling and shrinking as they drift southwest along the coast. They act as transport pods, bringing tropical species to places like New York and Massachusetts. Divers exploring a warm core ring off New Jersey might find brightly colored butterfly fish and triggerfish. Confused tourists from the Caribbean trapped in a spinning bubble of home. Conversely, when a meander pinches off to the south of the stream, it captures a core of cold, nutrient-rich shelf water and injects it into the warm, nutrient-poor Sargasso Sea. This is a cold core ring. These rings spin counterclockwise. They are biologically fascinating because they bring a massive injection of nutrients into the barren blue desert. The cold water in the center supports a bloom of phytoplankton, which attracts zooplankton and small fish. A cold core ring becomes a pop-up restaurant in the open ocean. Tuna, swordfish, and sharks converge on these rings to feed. Satellite imagery shows them as green swirls of life against the blue background. They eventually warm up and dissolve, but for a few months, they are hotspots of biological activity, spinning silos of food in the famine of the deep. Beneath the warm, northward-flowing Gulf Stream lies a secret, opposing force: the deep western boundary current. This is a river of cold, dense water that flows south, hugging the bottom of the continental slope. It is part of the global conveyor belt, carrying icy water from the Arctic down toward the equator. This creates a vertical shear in the ocean. A submarine diving through the Gulf Stream would first be pushed north by the warm surface current. But as it descended past 3,000 feet, it would hit the cold layer and be pushed south. The friction between these two opposing giants creates internal waves and turbulence in the deep, mixing the layers of the ocean. It is a dual carriageway, with heat moving north in the sun and cold moving south in the dark, balancing the planet's temperature in a continuous vertical loop. The interaction between the warm Gulf Stream and the cold atmosphere above it creates a breeding ground for some of the most violent weather on Earth, particularly off the coast of Cape Hatteras. This region is known as the graveyard of the Atlantic. In the winter, cold, dry air masses from the Canadian continent slide off the land and hit the steaming hot water of the stream. The temperature difference can be over 40 degrees. This thermal shock transfers massive amounts of energy into the atmosphere, causing low-pressure systems to deepen explosively. This phenomenon is called bombogenesis, or a bomb cyclone. The storm feeds on the heat of the river, spinning up hurricane-force winds in a matter of hours. The Gulf Stream is the fuel tank for these nor'easters, providing the moisture and the energy that buries New England in snow and batters the coast with waves. The salinity of the Gulf Stream is a key factor in its buoyancy and its survival as a distinct current. The water originates in the tropics, where the heat of the sun causes massive evaporation. When water evaporates, the salt is left behind, making the remaining water saltier and denser. However, because the water is so warm, thermal expansion makes it less dense than the cold water to the north. This creates a complex interplay of density. The warm, salty water of the stream floats on top of the cold, fresher water of the North Atlantic. It resists mixing. This density barrier is what keeps the walls of the river intact. If the stream were to cool down significantly, or if the surrounding ocean were to become saltier, the walls would crumble and the river would dissolve into the sea. The friction of the Gulf Stream moving against the surrounding water creates a phenomenon known as bioluminescence shear. At night, the turbulence at the edges of the current can agitate the microscopic dinoflagellates, the firefly plankton of the sea. These organisms flash blue-green when disturbed. On a dark, moonless night, the boundary of the Gulf Stream can sometimes be seen as a glowing line in the water, a ribbon of cold fire stretching to the horizon. Ships cutting through the current leave wakes that glow with an eerie intensity, the propellers churning up the light-producing creatures. It is a visual reminder of the energy contained in the flow, a river of light that marks the path of the heat through the darkness of the ocean. The acoustic properties of the Gulf Stream create a unique environment for sound, known as a sound channel. The temperature and pressure gradients within the current bend sound waves, trapping them in a layer where they can travel for hundreds of miles without losing energy. During the Cold War, submarines used the Gulf Stream as a strategic highway. A submarine could hide in the thermal layers of the current, which would reflect and scatter sonar pings, making the vessel invisible to surface ships. Or it could sit in the sound channel and listen to the noises of the entire ocean basin. The stream creates acoustic shadows, blind spots where sound cannot reach, providing a cloak of silence for the silent hunters of the deep who ride the current like a quiet elevator. Finally, we must consider the romantic and scientific history of drift bottles in the Gulf Stream. For centuries, sailors and scientists have thrown bottles with messages into the current to track its speed and direction. These drift bottles have washed up on the shores of Ireland, Scotland, and Norway, carrying notes from the Caribbean or the American coast. But nature has its own drift bottles, the sea hearts, or Entada gigas. These are large, woody seeds from a tropical vine that grows in the rainforests of Central America. They fall into the rivers, drift into the Gulf Stream, and float across the Atlantic. They are polished by the sand and the sea until they look like dark, wooden hearts. They frequently wash up on the beaches of Northern Europe, where for centuries they were considered lucky charms or fairy eggs. These seeds are the botanical proof of the stream's connection, linking the jungle to the fjord through the silent, persistent drift of the ocean river. Swimming through the high-velocity core of the Gulf Stream is one of the ocean's most formidable athletes, the Atlantic bluefin tuna. These are not merely fish, they are warm-blooded torpedoes that can weigh upwards of 1,500 pounds, built of solid muscle and metallic skin that shimmers like polished chrome in the sun. The Gulf Stream acts as their primary migratory highway, a conveyor belt that allows them to travel from their spawning grounds in the Gulf of Mexico to the feeding grounds of the North Atlantic with minimal energy expenditure. Because the tuna possesses a specialized circulatory system known as a counter-current heat exchanger, it can maintain a body temperature significantly higher than the surrounding water, sometimes by as much as 20 degrees Fahrenheit. This internal furnace allows their muscles to fire with explosive power even in the cold, deep water found at the edges of the stream. When a school of bluefin enters the current, they are effectively riding a heated, moving walkway, surfing the hydrodynamic front of the river to cover thousands of miles in a matter of weeks. They move with a stiffness that is deceptive, their tails vibrating at high frequencies to propel them through the blue void, guided by the temperature gradient of the water, as if it were a roadmap laid out in degrees of heat. Patrolling the sharp thermal boundaries where the warm Gulf Stream meets the cold slope, water is the swordfish, a predator that has evolved to conquer the darkness of the temperature break. The walls of the Gulf Stream are hunting grounds because the mixing of water masses concentrates baitfish and squid. The swordfish spends its days in the freezing depths, sometimes diving down to 2,000 feet, but rises at night to hunt in the warm surface waters of the stream. To survive this extreme thermal shock, going from near freezing to tropical temperatures in minutes, the swordfish possesses a specialized heating organ located directly behind its eyes and brain. This tissue, rich in mitochondria, generates heat to keep the eyes warm and functioning at peak efficiency, while the rest of the body remains cold. This brain heater gives the swordfish a massive advantage. Its eyes can process visual information 10 times faster than the cold-blooded prey it hunts. It is a hunter with heated vision, slashing its bill through the boundary waters of the Gulf Stream, striking at shadows that are too slow to react to the warm-eyed ghost emerging from the deep. As the Gulf Stream pushes further north, passing the coast of New England and reaching the Grand Banks of Newfoundland, it encounters its cold nemesis, the Labrador Current. This is a river of freezing, low salinity water flowing south from the Arctic Ocean. When the steaming, tropical water of the Gulf Stream collides with the icy breath of the Labrador Current. It creates one of the densest and most persistent fog banks on Earth. The warm, moist air above the stream is instantly cooled by the Arctic water, causing the humidity to condense into a thick, suffocating blanket of white vapor. This is known as sea smoke or advection fog. It can reduce visibility to zero in a matter of seconds, turning a bright afternoon into a blind grey twilight. For centuries, this fog has been the terror of mariners, muffling the sound of foghorns and hiding the hulls of fishing boats. The silence inside the fog bank is heavy and wet, a sensory deprivation tank created by the thermodynamic war between the tropics and the pole. This intersection of currents off Newfoundland is also the place where the Gulf Stream acts as the terminator for icebergs. The icebergs that carve off the glaciers of Greenland drift south on the Labrador Current, majestic cathedrals of white ice moving silently through the shipping lanes. But when they hit the wall of the Gulf Stream, their journey ends. The warm water attacks the ice, melting it at a ferocious rate. The thermal shock causes the icebergs to crack and fracture, releasing air bubbles that have been trapped in the ice for 10,000 years. This release creates a distinct fizzy popping sound known as Berg Seltzer, which can be heard by sonar and even by sailors on deck. The Gulf Stream effectively sets a southern limit for the ice, a thermal barrier that protects the central Atlantic from being overrun by frozen wanderers. It is a graveyard for the ice, where the frozen history of the Arctic melts into the salty, tropical future of the Atlantic circulation. Beneath the surface of the Gulf Stream, deep on the ocean floor of the Blake Plateau off the southeastern United States, lies a hidden world of deep water coral reefs. These are not the colorful, sun-drenched reefs of the Caribbean, but ghostly white thickets of Lophelia pertusa that live in total darkness. These corals do not have symbiotic algae to create food from sunlight. Instead, they rely entirely on the current. The Gulf Stream sweeps over the plateau, carrying a constant drift of organic particles and marine snow. The corals extend their delicate, translucent polyps into the flow, catching the food as it rushes past. These reefs have been growing for thousands of years, building massive mounds of calcium carbonate that can be hundreds of feet tall. They are the cities of the stream, providing habitat for wreckfish, crabs, and sharks in the cold, dark water beneath the warm river. The current is their lifeline, a waiter that never stops serving, allowing a vibrant ecosystem to thrive in a desert of darkness. The historical significance of the Gulf Stream's speed is written in the logs of the triangle trade sailing routes. In the 17th and 18th centuries, captains quickly learned that fighting the stream was futile. A ship trying to sail south from New York to the Caribbean against the current could find itself stationary for days, even with a fair wind. The Gulf Stream flows north at about 4 knots in its core. A typical merchant ship of the era might only sail at 5 or 6 knots. This meant that sailing south was a grueling, slow crawl. As a result, the trade routes formed a clockwise loop, sail southeast to Africa and the Caribbean on the trade winds, and sail north and east back to Europe or America, riding the Gulf Stream. This circular flow of water dictated the flow of sugar, rum, timber, and tragically, enslaved people. The current was the invisible gear that turned the economy of the Atlantic world, a force of nature that decided the path of history by simply being too strong to swim against. The thermal energy of the Gulf Stream is the primary fuel source for the rapid intensification of Atlantic hurricanes. When a tropical storm moves over the core of the stream, it is like throwing gasoline on a fire. Hurricanes are heat engines. They extract energy from warm ocean water to power their winds. The Gulf Stream provides a deep, inexhaustible reservoir of high-octane heat. Unlike shallow pools of warm water that can be cooled by the churning of the storm, The Gulf Stream is warm to a depth of several thousand feet. The storm can churn the water as much as it wants, but it will only bring up more warm water. This allows storms to explode in strength, sometimes jumping from a Category 1 to a Category 4 in a single night. The stream is a high-energy runway for these tempests, guiding them up the coast and feeding them the thermal power they need to batter the mid-latitudes with tropical fury. The reproductive cycle of the European eel relies entirely on the passive drift of the Gulf Stream to return the next generation to the rivers of the continent. After the adult eels spawn and die in the Sargasso Sea, their larvae, known as leptocephali, hatch into the warm water. These larvae are transparent, leaf-shaped creatures that look nothing like eels. They are poor swimmers, incapable of crossing the ocean on their own. Instead, they drift into the Gulf Stream and surrender to the flow. They spend up to 3 years drifting in the current, slowly crossing the Atlantic from west to east. They are suspended in the blue water, invisible to predators, eating marine snow as the river carries them thousands of miles to the estuaries of Europe. The Gulf Stream is their nursery and their vehicle, a cradle that rocks them gently across the abyss until they are strong enough to swim up the rivers of France, Spain, and Ireland. When these transparent larvae finally reach the coastal shelf of Europe or North America, they undergo a metamorphosis triggered by the change in water chemistry, transforming into glass eels. They develop a cylindrical shape but remain completely see-through, a final camouflage before entering the dangerous, muddy waters of the rivers. Millions of glass eels arrive in the estuaries on the high tides, riding the last pulses of the Gulf Stream's influence. At this stage, they develop pigment, turning dark grey or brown to match the river bottom, becoming elvers. This journey, from the Sargasso to the stream, and from the stream to the river, connects the deep, salty ocean gyre to the freshwater streams of the continents, a biological thread woven by the current that ties the mountains to the middle of the sea. The atmospheric partner of the Gulf Stream is the Azores High, a semi-permanent high-pressure system that sits over the eastern Atlantic. The clockwise winds generated by this pressure system are the driving force that pushes the Gulf Stream against the American coast and then steers it toward Europe. This interaction is a dance between the air and the water. When the Azores High shifts or weakens, the path of the Gulf Stream wobbles. The wind stress on the ocean surface imparts the momentum that keeps the gyre spinning. It is a reminder that the ocean current is not just a product of water, but of the sky. The trade winds push the water west, and the westerlies push it east, creating the Great Wheel of the North Atlantic. The Gulf Stream is simply the western rim of this wheel, spun by the invisible hand of the atmosphere. The navigational challenge of measuring the Gulf Stream before the invention of accurate chronometers was a source of immense frustration for sailors. To find their longitude, their east-west position, sailors needed to know the exact time, which required a clock that could keep time on a rolling ship. Before the chronometer, they relied on dead reckoning, estimating their speed and direction. But the Gulf Stream introduced a massive, invisible error. A captain might calculate that he had sailed 100 miles south, but the current had pushed him 50 miles north without him feeling it. This led to the longitude problem, where ships would miss islands or run aground because the ocean itself had moved beneath them. The Gulf Stream was a ghost in the mathematics of navigation, a variable that could not be solved until humanity learned to carry time in a box. At the distinct geographical point of Cape Hatteras, North Carolina, the Gulf Stream collides with the southerly flowing slope waters in a chaotic, turbulent mixing zone known as the Point. This is one of the most dynamic fishing grounds in the world. The collision of the northbound tropical water and the southbound cool water creates visible rip lines, whirlpools, and upwellings that bring nutrient-rich sediment to the surface. The watercolor changes abruptly from the murky green of the coast to the electric blue of the stream. This mixing zone stimulates a massive bloom of phytoplankton, which attracts baitfish, which in turn attracts the apex predators. Marlin, sailfish, and tuna congregate here in a feeding frenzy. It is an oceanic crossroads where the traffic of the entire Atlantic seems to merge, creating a biological traffic jam fueled by the friction of the currents. Soaring above the warm waters of the stream are the flying fish, creatures that have evolved to escape the predators below by taking to the air. These fish have enlarged pectoral fins that act as wings. When threatened by a tuna or a dolphin, the flying fish accelerates toward the surface, breaking the tension with a powerful flick of its tail. It spreads its fins and glides, using the updrafts of warm air rising from the Gulf Stream to extend its flight. They can glide for hundreds of feet, skimming just above the waves. The warm air over the current provides better lift than the cold air over the shelf water. To a sailor on deck, they look like flocks of silver birds bursting from the sea, flashing in the sun before splashing back down into the indigo deep. They are the aviators of the current, bridging the gap between the hydrodynamics of the water and the aerodynamics of the wind. In the Gulf of Mexico, the precursor to the Gulf Stream, the loop current, is prone to a phenomenon known as eddy shedding. The loop grows and extends northward until it becomes unstable, eventually pinching off a massive clockwise spinning ring of warm water that drifts westward toward Texas. These eddies are colossal, rotating heat bombs that can be hundreds of miles across. For the offshore oil industry, these eddies are a nightmare. The currents within a shed eddy can be strong enough to stress the risers and cables of oil rigs, forcing them to shut down operations. The loop current eddies are deep and powerful, retaining their spin for months as they slowly die in the Western Gulf. They are the children of the stream, orphan vortices that carry the DNA of the Caribbean current into the stagnant corners of the Gulf. The geological impact of the Gulf Stream is visible in the erosion of the ocean floor, particularly at a feature known as the Charleston Bump. This is a ridge of hard, rocky bottom on the Blake Plateau that rises into the path of the stream like a ramp. When the massive volume of water hits this bump, it is deflected offshore, creating a permanent meander or ripple in the current's path. This deflection causes the stream to scour the seabed, stripping away sediment and leaving bare rock. The Charleston Gyre forms in the lee of this bump, a semi-permanent eddy that traps larvae and nutrients. The stream is not just flowing over the earth, it is shaping it, acting as a liquid sandpaper that has polished the continental slope for millions of years, carving its own groove into the crust of the planet. Along the inner edge of the Gulf Stream, where the blue water meets the green shelf water, there exists a permanent chlorophyll front. This is a narrow band of high productivity where the friction of the two currents mixes the water layers. The turbulence brings nitrates and phosphates from the deep up to the light, fueling a constant bloom of algae. From space, this looks like a ribbon of green dye running alongside the blue highway. This green river is the base of the food chain for the coastal ecosystem. Small fish and squid thrive here, feeding on the plankton. It is a linear oasis, a long, thin garden that grows on the edge of the moving water, proving that the friction between two worlds is often where life is most abundant. The North Atlantic right whale, one of the most endangered whales on the planet, has a complicated relationship with the Gulf Stream. These whales prefer the cold, copepod-rich waters of the continental shelf and generally avoid the warm, sterile waters of the stream itself. However, to migrate from their feeding grounds in Canada to their calving grounds in Florida, they must navigate the edges of the current. The stream acts as a barrier, Mothers with calves must stay in the cooler, nearshore waters to avoid the thermal stress and the strong opposing current of the stream. This forces them into the busy shipping lanes along the coast, the urban ocean. The Gulf Stream effectively pens them in, squeezing their migration corridor between the land and the lethal heat of the river, shaping the geography of their survival. Hiding beneath the floating mats of sargassum weed in the stream is the mahi-mahi, or dolphin fish, a predator that embodies the golden energy of the surface. These fish are brilliantly colored in neon greens, yellows, and blues, matching the dappled light of the sun filtering through the weed. They grow with astonishing speed, one of the fastest growth rates of any fish, fueled by the abundance of life in the weed lines. A mahi-mahi can grow from a tiny larva to a 20-pound predator in less than a year. They live life in the fast lane of the current, constantly swimming, constantly eating. To a fisherman, finding a weed line in the Gulf Stream is finding gold, for beneath the yellow vegetation lies a school of these frenetic, colorful hunters, darting through the shadows of the drifting forest. The immense thermal energy difference between the warm surface water of the Gulf Stream and the cold, deep water beneath it represents a potential source of renewable energy known as Ocean Thermal Energy Conversion, OTEC. Engineers dream of using this temperature gradient to drive turbines. By pumping the warm surface water to boil a fluid with a low boiling point, like ammonia, and using the cold, deep water to condense the vapor back into liquid, a heat engine could generate electricity 24 hours a day. The Gulf Stream is essentially a massive, recharging battery. The energy contained in the temperature difference of the Florida Straits alone is theoretically enough to power the entire state of Florida. It is a silent, blue power plant that runs on nothing but the sun and the circulation of the earth, waiting for technology to catch up to its potential. Finally, we must consider the physics of sea level rise in relation to the Gulf Stream's speed. Because of the geostrophic balance, the tilt of the sea surface caused by the Earth's rotation and the current's flow, the water level is lower on the US coast than it is in the Sargasso Sea. The fast-moving current essentially pulls water away from the coast, keeping the sea level suppressed. However, scientists have observed that as the Gulf Stream slows down due to climate change, this pulling effect weakens. When the current slows, the hill of water in the Atlantic sloshes back toward the west, causing sea levels to rise along the American East Coast faster than the global average. The speed of the river is the only thing holding the ocean back from the land. As the river gets sleepy and sluggish, the water begins to reclaim the shore, a hydraulic consequence of a tired engine easing off the throttle. Floating on the surface of this indigo highway, carried along by the relentless push of the water, is a creature that looks like a festive balloon, but carries a venomous secret: the Portuguese man-o'-war. While often mistaken for a jellyfish, this organism is actually a siphonophore, a colonial animal made up of 4 distinct types of polyps that function together as a single entity. The most visible part is the pneumatophore, a gas-filled bladder that sits above the water like a blue or violet sail. This sail catches the wind, allowing the man-o'-war to travel across the ocean. However, the Gulf Stream plays a crucial role in their distribution. The species is dimorphic regarding its sail. Some are left-handed and some are right-handed, meaning the sail is angled to push them either to the left or the right of the wind direction. This biological design ensures that the population is split, preventing the entire fleet from being washed onto the same beach during a storm. In the Gulf Stream, the interaction between the wind and the current sorts these creatures, scattering them across the Atlantic. Beneath the beautiful iridescent float, Tentacles can trail for up to 165 feet, forming a deadly drift net of stinging cells that paralyzes small fish. These tentacles are invisible threads of pain in the blue water, a drifting minefield that moves with the silent, wind-driven purpose of the current. Beneath the surface of the stream, in the deep canyons of the continental slope, where the warm water rubs against the cold earth, lives the golden crab. This large, slow-moving crustacean is a true denizen of the Gulf Stream's underbelly. It lives at depths of over 2,000 feet, in the cold, dark water that flows beneath the tropical surface layer. The golden crab is named for its shell, which is a pale, creamy apricot color, appearing golden in the lights of submersibles. These crabs are specialized scavengers that rely on the marine snow and the larger carcasses that rain down from the productive surface waters of the stream. Because the current above is so strong, it sweeps organic matter off the shallow shelf and deposits it into the deep canyons, creating a nutrient trap. The crabs patrol these deep, muddy valleys, walking on long, spindly legs that distribute their weight on the soft sediment, feeding on the detritus of the river above. They are the janitors of the deep stream, turning the waste of the pelagic world into life in the crushing dark. The Gulf Stream is also the stage for a massive, tragic ecological event known as the Great Tilefish Die-Off of 1882. The tilefish is a colorful, bottom-dwelling fish that lives in a very specific temperature band along the continental shelf, right where the warm Gulf Stream water meets the cold slope water. They require water between 48 and 57 degrees Fahrenheit. In the spring of 1882, a violent gale disrupted the path of the Gulf Stream, forcing it away from the shelf and allowing a massive intrusion of freezing Arctic water to flood the tilefish habitat. The result was catastrophic. The thermal shock killed billions of fish. Ships reported sailing for hours through a sea of dead floating tilefish that stretched from horizon to horizon. The population was decimated so thoroughly that scientists thought the species had gone extinct. It took decades for the Gulf Stream to stabilize and for the tilefish to slowly recolonize their narrow band of habitable temperature. It serves as a stark reminder of how fragile life is at the boundaries of these massive currents. A simple wobble in the river's path can wipe out an entire species in a matter of days. As the Gulf Stream travels east, it begins to interact with the seabed topography of the Mid-Atlantic Ridge, a massive underwater mountain range that runs down the center of the ocean. When the deep layers of the current hit these jagged peaks, it creates a phenomenon called topographic steering. The mountains force the water to bend and twist, generating deep ocean eddies and internal waves that can be hundreds of feet high. These internal waves never break the surface, but they mix the layers of the ocean, bringing cold, nutrient-rich water up from the bottom. This mixing over the ridge creates a chlorophyll oasis in the middle of the Atlantic. Satellite imagery shows blooms of phytoplankton tracing the shape of the underwater mountains. The Gulf Stream essentially stubs its toe on the mountains, and the resulting turbulence feeds the whales and seabirds that congregate in the middle of nowhere, miles from any shore. The transition of the Gulf Stream into the North Atlantic Drift is a moment of diffusion, where the river loses its banks and becomes a fan. Southeast of Newfoundland, the distinct, high-velocity jet of the stream begins to widen and slow down. It splits into several branches, like a river delta entering the sea. One branch turns south toward the Canary Islands, while the main branch continues northeast toward Europe. This widening creates a vast area of slope water that is a mixing bowl of temperatures. It is no longer a single blue highway, but a complex tapestry of warm filaments and cold swirls. This transition zone is critical for the climate of Europe. As the current spreads out, it exposes more surface area to the atmosphere, releasing the last of its tropical heat to the westerly winds. This final release is what keeps the rains of Ireland soft and the winters of Scotland mild, a dying breath of heat from the Caribbean that warms a continent thousands of miles away. Embedded in the physics of the Gulf Stream is the Atlantic Meridional Overturning Circulation, or AMOK, the global conveyor belt of which the stream is the upper limb. The warm, salty water carried north by the stream eventually reaches the Nordic seas. Here, in the freezing cold of the Arctic winter, the water cools rapidly. Because it is salty from evaporation in the tropics, and now freezing cold, it becomes incredibly dense. It becomes heavier than the water around it and sinks, plunging down to the bottom of the ocean in massive underwater waterfalls known as chimneys. This sinking water pulls the Gulf Stream north to replace it. It is a planetary pump. If this sinking were to stop, perhaps due to melting ice sheets, freshening the water, and making it too light to sink, the pump would fail, and the Gulf Stream would weaken or stop. This delicate balance of salt and temperature is the heartbeat of the world's climate, a rhythm of sinking water that pulls the warmth of the tropics toward the pole. The black hole of the open ocean is a term sometimes used by ornithologists to describe the core of the Gulf Stream in the central Atlantic. Because the water in the center of the stream is so nutrient-poor, there is very little for seabirds to eat. While the edges of the stream are teeming with life, the center is often a biological desert. Seabirds like storm petrels and shearwaters will actively fly around the core, sticking to the cooler, richer waters on the periphery. A ship sailing down the exact center of the stream might not see a single bird for days. It is a zone of solitude, a blue void where the water is too clear and too empty to support the flocks that cloud the sky over the fishing grounds of the Grand Banks. Floating delicately in the upper layers of the stream is the paper nautilus, or argonaut. This is not a true nautilus, but a species of octopus that has evolved a unique way to protect its eggs. The female argonaut secretes a paper-thin white shell from glands in 2 of her tentacles. She lives inside this shell, using it as a brood chamber and a ballast tank. She can trap air bubbles in the top of the shell to maintain neutral buoyancy, allowing her to drift effortlessly in the Gulf Stream without swimming. She rides the current, clutching her shell, feeding on small mollusks and crustaceans. The male argonaut is tiny, shellless, and lives only to reproduce. The female is a lonely traveler, a drifter in a boat of her own making, carried by the warm water into the northern latitudes where her fragile shell sometimes washes ashore, a mystery to beachcombers who find the egg case of an octopus far from any reef. The Rossby waves are planetary-scale waves that move through the ocean, affecting the path of the Gulf Stream. These are not waves on the surface, but undulations of the thermocline, the boundary between warm and cold water deep in the ocean. They are driven by the rotation of the Earth and travel from east to west. When a Rossby wave hits the Gulf Stream, it can cause the current to meander or shift its position by miles. These waves move incredibly slowly, taking months or years to cross the Atlantic. They are the slow-motion breathing of the ocean basin. The path of the Gulf Stream is effectively dancing to a rhythm set by the spinning of the planet, undulating in response to waves that are thousands of miles long and invisible from the surface. The Sargasso Sea, the gyre created by the Gulf Stream, has sadly become a trap for more than just seaweed. It is a convergence zone for microplastics. The same currents that concentrate the sargassum weed also gather the floating debris of human civilization. The plastic breaks down into tiny particles under the sun, turning the water into a synthetic soup. The sargassum mats now act as filters, trapping bottle caps and fishing line. The juvenile turtles that rely on the weed for safety are now growing up in a nursery of trash. The Gulf Stream acts as a conveyor belt for pollution, sweeping garbage from the coasts of North America and depositing it in the calm center of the ocean, creating a silent, invisible smog of plastic that drifts alongside the golden algae. The ocean sunfish, or mola mola, utilizes the Gulf Stream as a thermal recharging station. These massive, disc-shaped fish dive deep into the cold waters below the stream to hunt jellyfish, reaching depths where the temperature is near freezing. After a hunt, their body temperature drops and their muscles slow down. To recover, they ascend to the warm surface waters of the Gulf Stream. They turn on their sides, presenting their massive flat bodies to the sun, floating like basking sharks. This behavior, known as thermal recharging, allows them to absorb heat from both the sun and the warm water of the current. They are solar-powered hunters, using the heat of the stream to fuel their dives into the abyss, drifting passively while they warm up for the next descent. The acoustic landscape of the Gulf Stream is influenced by the afternoon effect. As the sun heats the surface of the water during the day, a distinct thermal layer forms. Sound waves generated at the surface by ships or sonar are bent downward by this warm layer, creating a shadow zone where submarines can hide. In the late afternoon, when the surface is hottest, this effect is strongest. A submarine sitting just below the thermal layer is invisible to surface sonar. The Gulf Stream, with its intense heat, amplifies this effect. It provides a blanket of thermal noise that masks the sounds of the deep, creating a game of hide and seek played with the physics of sound and temperature. The historical impact of the Gulf Stream on the wine industry of Europe is a testament to its climatic power. The stream warms the prevailing westerly winds that blow over Europe. This warmth extends the growing season and prevents hard frosts in regions like Bordeaux and the Rhineland. Without the Gulf Stream, these regions would have climates similar to Newfoundland or Labrador, which are at the same latitude. Grapes would not grow. The vineyards of France and Germany are essentially heated by the Caribbean sun, transported across the ocean by the current. Every bottle of European wine is a product of the Gulf Stream, a distillation of the heat carried north by the silent river of salt. The phenomenon of loop current intrusion in the Gulf of Mexico sometimes sees the current pushing much further north than usual, reaching the continental shelf of Florida and Alabama. When this happens, it brings blue, clear water right up to the beaches of the Panhandle. Tourists are delighted by the Caribbean-like water, but for the local ecosystem, it is a shock. The nutrient-poor water replaces the rich coastal water, temporarily reducing the catch for fishermen. However, it also brings sport fish like sailfish and wahoo within sight of the piers. It is a temporary invasion of the tropics, a pulse of the stream that momentarily rewrites the biological map of the coast. The Great Salinity Anomaly was a massive pulse of fresh water that circulated the North Atlantic in the 1970s, tracking the path of the subpolar gyre and interacting with the Gulf Stream. This slug of fresh water, likely from melting sea ice in the Arctic, acted as a tracer, allowing scientists to time the circulation of the ocean. It took over a decade to travel around the basin. When it encountered the Gulf Stream, the fresh water altered the density of the current, briefly slowing the sinking of water in the north. It was a warning shot from the climate system, showing how a melting Arctic can throw a wrench into the gears of the global heat engine, slowing the river that warms the world. The deep ocean floor beneath the Gulf Stream extension, specifically the Porcupine Abyssal Plain off the coast of Ireland, is subject to a benthic storm season. When the surface waters of the stream bloom with plankton in the spring, a massive amount of organic matter, phytodetritus, rains down to the abyss 15,000 feet below. This marine snow arrives in a sudden pulse, carpeting the seafloor in green fluff. This triggers an explosion of life in the deep. The Amperima event was a famous instance where the population of a small purple sea cucumber called amperima, exploded in numbers to feast on the detritus. They marched across the abyssal plain in the millions, consuming the fallout from the river above. The biology of the deepest, darkest mud is directly tied to the flow of the sunlit stream miles overhead. The modern shipping industry uses the Gulf Stream with the same strategic planning as the sailing captains of old, but with higher stakes. Massive container ships heading from the US to Europe will deliberately steer into the core of the stream to gain an extra 3 or 4 knots of speed, saving thousands of gallons of fuel and shaving a day off the transit. Conversely, ships heading south will hug the coast to avoid it. This creates a highway system in the ocean. Weather routing services provide captains with real-time satellite maps of the stream's eddies and meanders. A captain will steer a 1,000-foot ship to catch the edge of a warm core ring to get a slingshot boost. The stream is an economic asset, a free source of energy that reduces the carbon footprint of global trade, provided you know exactly where the river is flowing that day. The distinct blue color of the Gulf Stream is scientifically classified as Forel-Eul's scale 1 or 2, the bluest water possible in nature. This clarity is due to the oligotrophic nature of the water, meaning it has very low nutrient levels. In the center of the stream, light can penetrate to depths of over 300 feet. This deep light penetration allows for a unique visual environment. Deep-sea predators that hunt in the stream often have eyes tuned to the specific wavelength of blue light that filters down. Camouflage in the stream relies on counter-illumination, where fish produce light on their bellies to match the downwelling sunlight, blending in with the bright surface when seen from below. In the crystal-clear water of the stream, hiding is impossible without light. You must become part of the shine. The interaction of the Gulf Stream with the atmosphere creates a cloud line that is often visible from space. As the warm, humid air rises from the current, it hits the cooler air above and condenses into a line of cumulus clouds that perfectly traces the path of the water. Sailors call this the pathway of the gods. On a clear day, a ship can navigate by looking at the sky. The line of fluffy white clouds marks the location of the warm water, even if the sea itself looks uniform. Beneath these clouds, rain showers are frequent, returning the evaporated water to the ocean in a localized hydrological cycle that travels with the current, a private weather system that hovers over the river. Finally, we look at the paleoclimatology of the stream through the lens of the Younger Dryas event. About 12,900 years ago, the Gulf Stream system suddenly shut down. A massive glacial lake in North America burst its dam, flooding the North Atlantic with fresh water. This stopped the sinking of the dense water in the north, halting the conveyor belt. Europe plunged back into an ice age almost overnight. The glaciers advanced, and the forests died. It lasted for over 1,000 years before the current restarted. This event is the ghost story of climate science, a reminder that the Gulf Stream is not a permanent fixture, but a fragile switch. It can be turned off. The warmth we enjoy, the stable climate of the Holocene, is a gift of the moving water, a gift that requires the balance of salt and ice to remain flowing. The physics behind the Gulf Stream's peculiar habit of hugging the western edge of the ocean basin is governed by a planetary force known as western boundary intensification. If the Earth did not rotate, the warm water from the tropics would flow north in a broad, lazy sheet, evenly distributed across the Atlantic. However, because the Earth spins to the east, the Coriolis force increases with latitude. This variation creates a pileup of potential vorticity that compresses the gyre against the American continental shelf. It forces the water into a narrow, fast-moving channel on the west, while the return flow on the eastern side of the ocean, the Canary Current, is wide, slow, and shallow. The Gulf Stream is essentially being squeezed against the continent by the rotation of the planet. This intensification is why the stream is a jet rather than a drift. It is the ocean's way of conserving angular momentum, a balancing act of physics that turns a gentle circulation into a liquid whip, lashing out from the tropics with concentrated power that defines the asymmetry of the entire Atlantic basin. Between this racing blue jet and the coastline of the northeastern United States lies a distinct and often overlooked body of water known as the Slope Sea. This is a wedge of water trapped between the Gulf Stream and the continental shelf, functioning as a buffer zone. The water here is a mix of coastal runoff and leakage from the stream, creating a unique salinity and temperature profile that is neither fully oceanic nor fully coastal. It is a turbulent, mixing bowl where warm filaments from the stream curl backward and cold water from the shelf pushes outward. The Slope Sea acts as a biological nursery for many commercially important fish species, sheltered from the high-velocity transport of the main current, but warm enough to support rapid growth. It is a gyre within a gyre, a smaller, counter-rotating eddy that exists in the shadow of the giant, collecting the strays and the drifters that fall off the edge of the superhighway. The edges of the Gulf Stream are not smooth walls, but fraying tapestries of water known as shingles or filaments. These are thin, finger-like projections of warm water that break away from the main current and intrude onto the cold continental shelf. Seen from satellite thermal imaging, they look like flames licking the coast. These filaments are short-lived, often dissipating in a few days, but they transfer massive amounts of heat and salt onto the shelf. For a lobster or a crab living on the bottom of the shelf, the arrival of a shingle is a sudden, confusing heat wave. The temperature on the bottom can jump 10 degrees in an hour. These intrusions can trigger out-of-season spawning events or cause sudden migrations, confusing the biological clocks of the local fauna with a false spring delivered by the leaking energy of the stream. The life cycle of a cold core ring, once it has severed ties with the Gulf Stream, becomes a slow, spiraling journey into biological decay. When the ring first forms, trapping a core of cold, nutrient-rich water, it is a boomtown of plankton and fish. But as the ring drifts south into the Sargasso Sea, it is cut off from new nutrients. The plankton bloom consumes all the available food, and the water begins to clear. The fish inside are trapped in a shrinking prison. As the months pass, the ring spins down, losing its momentum to friction and its cold core to the surrounding warmth. It slowly sinks and dissolves. The population of the ring starves or is eaten by the predators of the Sargasso. It is a dying world, a bubble of productivity that slowly fades into the blue desert, leaving behind only the memory of its spin in the turbulence of the deep water. Hidden within the floating mats of sargassum weed that ride the current is a master of disguise, the sargassum frogfish, histrio. This fish has evolved to become invisible. Its skin is covered in fleshy tabs and flaps that perfectly mimic the leaves and gas bladders of the weed. Its color can shift from golden yellow to mottled brown to match the specific patch of algae it inhabits. It does not swim in the traditional sense. It uses its pectoral fins like hands to climb through the tangled vegetation. The frogfish is a voracious ambush predator, capable of expanding its mouth to swallow prey as large as itself. It sits motionless in the drifting canopy, a piece of the forest that has grown eyes and a mouth, waiting for a shrimp or a small fish to mistake it for a safe harbor in the fast-moving stream. Rising from the depths at night to feed in the rich waters of the stream is the neon flying squid, Omostrephus bartrami. These cephalopods are named for their ability to launch themselves out of the water and glide through the air to escape predators, similar to flying fish. They possess lateral membranes on their tentacles that act as wings. In the Gulf Stream, they use the current to migrate vast distances. They travel north with the warm water to feed and then return south to spawn. At night, they hunt in packs, their bodies flashing with bioluminescence. To a predator looking up from below, their glowing undersides match the moonlight. To a predator looking down, their dark backs match the deep. They are the phantoms of the current, jet propelling themselves through the water and the air, blurring the line between the ocean and the sky. Deep beneath the surface of the Gulf Stream, in the crushing darkness of the continental slope, lives the elusive Gervais beaked whale. This species is rarely seen alive and is known primarily from strandings and acoustic recordings. They prefer the deep, warm waters of the stream's edge. These whales are champion divers, descending to depths of over 3,000 feet to hunt squid using echolocation. They live in the acoustic shadow of the stream, where the noise of the current masks their clicks from predators like orcas. The Gulf Stream provides them with a corridor of deep, warm water that extends far into the temperate latitudes, allowing them to live a tropical lifestyle in the North Atlantic. They are the secret residents of the river's basement, breathing air, but living their lives in the eternal night beneath the flow. During the Second World War, the thermal properties of the Gulf Stream turned it into a strategic battlefield for U-boats. German submarine captains quickly learned to exploit the thermocline, the sharp boundary between the warm surface water of the stream and the cold water below. By positioning their U-boats just beneath this layer, they could become invisible to sonar. The density difference of the water layers would bounce the sonar pings of Allied destroyers back to the surface, hiding the submarine in a blind zone. The U-boats would ride the current north to save fuel, lying in wait for the convoys carrying supplies to Europe. The Gulf Stream became a place of silent, deadly hide-and-seek, where the physics of heat and sound were used as weapons in the battle for the Atlantic. The interaction of the Gulf Stream with the shifting sands of the Diamond Shoals off Cape Hatteras creates one of the most treacherous navigational hazards on Earth. Here, the northbound Gulf Stream collides head-on with the southbound Labrador Current extension. This collision causes sand to drop out of the water column, building massive, shifting underwater dunes that can rise to within feet of the surface. The shoals are constantly moving, reshaped by the violent currents. A ship channel that was safe yesterday might be a sandbar today. This dynamic geology has claimed thousands of ships, earning the area the name Graveyard of the Atlantic. The wrecks are quickly buried by the sand and then uncovered years later, ghostly hulls appearing and disappearing in the surf as the currents fight their eternal war over the shape of the bottom. The relationship between the Gulf Stream and the atmospheric jet stream is a complex dance of heat and wind known as air-sea coupling. The heat released by the Gulf Stream warms the atmosphere above it, causing the air to rise and expanding the height of the troposphere. This thermal mountain in the air can anchor the path of the high-altitude jet stream. In winter, the position of the Gulf Stream can steer storms across the Atlantic toward Europe. If the Gulf Stream shifts its path, the storm track shifts with it. The ocean is effectively guiding the wind. This coupling means that a change in the current's temperature off the coast of Carolina can dictate whether London gets rain or snow a week later. It is a planetary feedback loop where the water leads and the air follows. The historical record of the Little Ice Age, a period of cooling in Europe from the 14th to the 19th century, offers a glimpse into what happens when the Gulf Stream weakens. Climate proxies such as ice cores and tree rings suggest that the Atlantic circulation slowed down during this time. The winters in Europe became brutal. The Thames River in London froze over regularly, and glaciers advanced in the Alps. The heat pump of the Gulf Stream had turned down its dial. Crop failures and famines were common. This period serves as a historical case study for the climatic importance of the current. It wasn't a total shutdown, but merely a hesitation in the flow. Yet it was enough to freeze the heart of a continent and alter the course of human history. The Gulf Stream plays a critical role in the ventilation of the deep ocean, a process that delivers life-giving oxygen to the abyss. As the water moves north and cools, it absorbs massive amounts of oxygen from the atmosphere. Cold water holds more gas than warm water. When this water eventually sinks in the North Atlantic to form deep water, it carries this dissolved oxygen down with it. This deep water formation is the primary source of oxygen for the deep-sea organisms of the Atlantic. Without this injection of breath from the surface, the deep ocean would become anoxic and stagnant. The sponges, worms, and fish of the abyss are effectively breathing air that was captured by the Gulf Stream thousands of miles away and delivered via the slow, sinking elevator of the thermohaline circulation. The cultural impact of the Gulf Stream was immortalized in the dramatic painting The Gulf Stream by Winslow Homer, painted in 1899. The image depicts a lone man on a dismasted sloop, drifting in deep blue, shark-infested waters, seemingly doomed. Homer captured the dual nature of the current, its stunning, vibrant beauty, and its indifferent cruelty. The indigo water in the painting is rich and saturated, contrasting with the white foam and the grey sharks. It represents the stream as a force that cannot be tamed or pleaded with. The painting solidified the public perception of the Gulf Stream not just as a shipping lane, but as a wild, dangerous frontier where humanity is small and the water is deep, blue, and hungry. In the open waters of the stream, the Atlantic sailfish utilizes the current's walls for a specialized hunting technique. Sailfish are the fastest sprinters in the ocean, but they are also cooperative hunters. They work in packs to corral schools of baitfish. They use the sharp boundary of the Gulf Stream as a wall. They drive the baitfish against the thermal front or the surface, trapping them where they cannot escape. Once the bait is balled up, the sailfish take turns slashing through the school with their rough bills, stunning the fish before swallowing them. They flash iridescent colors, purple, blue, and silver, to communicate with each other and confuse the prey. It is a coordinated attack that relies on the hydrodynamics of the stream to limit the prey's escape routes, turning the current into a killing jar. The Gulf Stream acts as a thermal barrier for shark species, segregating the ocean into different zones of predation. Coastal sharks, like the blacktip and bull shark, prefer the warm, murky waters of the shelf and rarely cross the stream into the open ocean. Conversely, pelagic sharks like the oceanic whitetip and the blue shark stay in the deep blue waters of the stream and rarely venture onto the shelf. The wall of the stream keeps these populations apart. However, large tiger sharks have been tracked using the stream as a migration highway, riding the warm water north in the summer and returning south in the winter. For them, the stream is a bridge. For others, it is a fence. This invisible line dictates the community structure of the apex predators, deciding who eats whom in the hierarchy of the Atlantic. Within the Slope Sea, north of the Gulf Stream, a localized gyre often forms, rotating counterclockwise. This slope water gyre is driven by the friction of the Gulf Stream passing to the south. It acts as a retention bowl for plankton and larvae. Lobster larvae spawned on the edge of the continental shelf can be trapped in this gyre, kept close to home rather than being swept out to sea. This retention mechanism is crucial for the fisheries of New England. The gyre holds the biological wealth of the coast in a safe harbor of circulation, preventing the Gulf Stream from stripping the shelf bare of its next generation. It is a protective back eddy, a slow lane next to the express highway. Hidden in the depths beneath the Gulf Stream is a sleeping giant of biomass, the copepod Calanus finmarchicus. These tiny crustaceans are the rice of the ocean, the staple food for right whales and herring. In late summer, they undergo a process called diapause. They migrate down to depths of 2,000 feet or more, into the cold, dark water beneath the stream. There they enter a state of suspended animation, lowering their metabolism to near zero. They hang in the darkness for months, waiting for the spring phytoplankton bloom. The Gulf Stream flows over their heads, warm and active, while they sleep in the cellar. This vertical partitioning allows them to survive the winter famine, storing their energy in oil sacs that make them rich, fatty prizes for any deep-diving predator lucky enough to find their sleeping clouds. The mechanism of shelf break upwelling is driven by the passage of the Gulf Stream. As the current rubs against the edge of the continental shelf, the friction creates a suction effect known as Ekman transport. This pulls cold, nutrient-laden water up from the deep ocean and spills it onto the shelf. This upwelling fertilizes the sunlit waters, triggering blooms of algae that support the massive fisheries of the Grand Banks and George Bank. The Gulf Stream is the engine that powers this pump. It doesn't just transport heat, it mines the deep ocean for fertilizer, bringing the ancient nitrates of the abyss up to the surface to feed the cod and the haddock that have sustained nations for centuries. As the Gulf Stream reaches the eastern Atlantic, it flows into the Porcupine Sea Bight, a deep basin off the coast of Ireland. Here, the current slows and sheds its load of organic matter. The dying plankton and detritus from the long journey settle out of the water column, creating a thick layer of phytodetritus on the seafloor. This green sludge is a feast for deep-sea life. The seabed here is teeming with strange, gelatinous sea cucumbers and brittle stars that rely on the fallout from the stream. It is the end of the line for the biological energy captured in the Caribbean. The sun that shone on the Bahamas fuels the life in the dark mud off the coast of Galway, a transatlantic transfer of calories delivered by the silent river. Finally, the Gulf Stream undergoes a transformation as it passes Scotland and Norway, ceasing to be a singular stream and becoming the North Atlantic Drift. The distinct blue ribbon dissolves into a broad, sluggish movement of relatively warm water. The indigo color fades to a steely grey-green as it mixes with the nutrient-rich subpolar waters. The velocity drops, the walls vanish, and the heat is dispersed into the chaotic storms of the high latitudes. It is a gentle death for the river. It does not end with a waterfall or a crash, but with a slow diffusion, spreading its identity into the larger ocean until it is indistinguishable from the sea itself, having completed its task of warming the world and driving the cycle of life in the North Atlantic. The sheer physical weight of the Gulf Stream is a concept that defies ordinary human intuition, for it represents a massive displacement of mass that actually alters the shape of the Earth's crust. As the billions of tons of water flow northward, they exert a subtle but measurable pressure on the ocean floor. This phenomenon, known as ocean bottom pressure anomaly, fluctuates with the strength of the current. When the Gulf Stream is flowing at its peak velocity, the geostrophic balance requires a steeper slope of the sea surface, piling water up in the center of the gyre. This shifting mass of water is heavy enough to slightly depress the lithosphere, the rigid outer layer of the Earth. It is a river so mighty that it does not just carve a valley, it weighs down the planet, bending the rock beneath the ocean with the heavy, fluid burden of its circulation, a constant, silent massage of the Earth's skin by the muscles of the ocean. Drifting within the intricate microlayers of the stream is a fragile beauty known as the sea butterfly, or pteropod. These are tiny, swimming snails that have evolved a foot modified into two wing-like lobes that allow them to flutter through the water column. They construct delicate, translucent shells made of aragonite, a form of calcium carbonate. In the Gulf Stream, they drift in swarms that can number in the thousands per cubic meter. They are the potato chips of the sea, a vital food source for herring, mackerel, and even whales. However, they are also the canaries in the coal mine for ocean acidification. Because the Gulf Stream carries warm water, which can hold less carbon dioxide, it is generally safer for them. But as they drift north and the water cools, absorbing more gas, their shells are at risk of dissolving. They are glass sculptures drifting in a chemical river, fluttering their wings against the changing pH of the world, beautiful and brittle passengers on the conveyor belt. The geological history of the Gulf Stream is written in the massive piles of mud known as sediment drifts, specifically the Blake Ridge off the coast of the Carolinas. This ridge is not a mountain range formed by tectonic uplift, but a sculpture made of silt. For millions of years, the deep western boundary current, the cold countercurrent flowing beneath the Gulf Stream, has swept sediment along the ocean floor. The interaction between this deep current and the Gulf Stream above creates a quiet zone where the mud settles out of the water. Over eons, this has built a mountain of mud hundreds of miles long and thousands of feet high. Paleoceanographers drill into this ridge to read the layers. The size of the grains tells them how fast the current was moving 5 million years ago. It is a library of mud, built by the friction between the warm river and the cold deep, preserving the speed logs of the ocean in the silent dark. In the acoustic shadows of the Gulf Stream's thermal layers, the Trews-beaked whale finds a sanctuary for its sensitive hearing. These deep-diving mammals are notoriously shy and vulnerable to the sonar of naval vessels. The complex temperature gradients of the stream refract sound waves, creating zones of silence where sonar cannot penetrate effectively. The whales utilize these natural stealth corridors to rest and socialize. They dive to depths of over 3,000 feet to hunt squid, holding their breath for an hour, and then surface in the warm, choppy waters of the stream. They are the ghosts of the current, living in the blind spots of human technology, wrapped in a blanket of water that scrambles the noise of the industrial world. The interaction between the Gulf Stream and the atmosphere creates a phenomenon known as the marine atmospheric boundary layer, which is often visibly distinct to sailors. Because the water is so much warmer than the air, especially in winter, the air directly above, the surface becomes unstable and turbulent. This creates a layer of sea smoke or low-lying mist that hugs the surface of the current. Above this mist, the air might be clear. This creates a tunnel effect for ships, sailing through a corridor of vapor. This unstable air also refracts radar beams, allowing ships to see over the horizon, detecting vessels or land masses that should be physically invisible. It is a mirage generator, a trick of the light and heat that bends the visual horizon and allows sailors to glimpse the future of their course through the lens of the warm air. The sargassum swimming crab, Portunus sayi, is a permanent resident of the drifting weed mats in the stream, and it has evolved to be a master of the moving platform. Unlike other crabs that crawl on the bottom, this crab has paddle-like back legs adapted for swimming. Its shell is mottled with brown, yellow, and white patterns that perfectly match the sargassum leaves. It is an ambush predator, clinging to the weed as it drifts at 4 knots. It waits for small fish or shrimp to seek shelter in the weed, then strikes. If the weed mat is broken apart by waves, the crab simply swims through the blue void to the next raft. It is a nomadic hunter that never touches the solid earth, living its entire life suspended over 3 miles of water, clinging to a golden raft that is constantly traveling north. The recirculation gyres are massive, clockwise spinning eddies that sit to the south and east of the main Gulf Stream jet, acting as boosters for the current. The most famous is the Worthington Gyre. These systems collect water and feed it back into the main stream, increasing its volume. They act like flywheels, storing kinetic energy. The water in these gyres is deep and isothermal, the same temperature from the surface down to great depths. This deep reservoir of heat acts as a buffer, stabilizing the Gulf Stream against short-term weather changes. If a cold winter cools the surface, the gyre mixes the deep, warm water up, keeping the system running. They are the batteries of the circulation, silent spinning reserves that ensure the river never runs dry of heat. The optical properties of the Gulf Stream water are so distinct that they were used during the Cold War to track submarines using lasers. The blue light of a blue-green laser penetrates the clear, oligotrophic water of the stream, much better than the murky coastal water. This allowed for the development of LiDAR systems that could theoretically detect submerged objects from aircraft. The incredible transparency of the water, where a white disk can be seen at depths of 150 feet or more, means that the Gulf Stream is a window into the deep. Sunlight illuminates the mesopelagic zone much brighter here than elsewhere, influencing the vertical migration of plankton. The creatures of the deep stream must dive deeper during the day to find darkness than their cousins in the green coastal seas, driven down by the relentless clarity of the blue water. The Gulf Stream acts as a barrier to the dispersion of coastal larvae, creating a biological wall that separates the populations of marine animals on the shelf from those in the open ocean. Many coastal fish release their eggs into the water column. If these eggs drift too far and get swept into the high-velocity jet of the stream, they are lost, carried away to the deep Atlantic where they cannot survive. This is known as advective loss. To prevent this, many species have evolved to spawn in the back eddies and slow-moving gyres of the slope sea, ensuring their offspring stay on the continental shelf. The stream is a reaper of the careless, a force that strips the coast of genetic material if the timing of the spawn is not perfectly synchronized with the tides and the local currents. Deep within the sediment of the Bermuda Rise, far offshore, lies the fossil evidence of the Gulf Stream's shutdown modes. These are layers of distinctive red clay that originated in the Gulf of St. Lawrence. During ice ages, when the Gulf Stream was weak, this red clay drifted south and settled near Bermuda. During warm periods like today, the swift current washes this clay away or buries it under grey foraminifera ooze. By taking core samples of the mud, scientists can read the barcode of the climate. Alternating stripes of red and grey mud tell the story of the stream turning on and off over millions of years. It is a geological traffic light, recorded in the colour of the dirt on the bottom of the sea, showing us that the river we trust is not eternal, but a flickering feature of the interglacial warmth. The hatchetfish is a denizen of the twilight zone beneath the Gulf Stream that has mastered the art of disappearing against the downwelling light. These small silver fish have bodies that are impossibly thin, like a coin. Their bellies are lined with light-producing organs called photophores. As they swim in the clear water of the stream, looking up, a predator would see their silhouette against the sun. To counter this, the hatchetfish produces light from its belly that exactly matches the color and intensity of the sunlight filtering down. This is counter-illumination. In the crystal-clear blue of the Gulf Stream, where shadows are deadly, the hatchetfish survives by becoming a lamp, erasing its own shadow with biological photons. The slope water between the Gulf Stream and the coast acts as a dumping ground for terrestrial carbon. Rivers flow into the ocean, carrying leaves, soil, and dissolved carbon. The complex mixing at the edge of the stream, the subduction of shelf water beneath the current, injects this carbon into the deep ocean. The Gulf Stream effectively sequesters the runoff of the North American continent, pushing it down into the abyssal plain, where it can remain for centuries. This continental shelf pump is a vital part of the global carbon cycle. The stream is cleaning the continent, sweeping the organic dust of the forests and fields into the deep storage locker of the Atlantic. The intricate dance of the meander troughs creates localized zones of upwelling that attract tuna and billfish. As the stream curves, the centrifugal force pushes water outward, creating a low-pressure zone on the inside of the curve. This low pressure sucks cold, nutrient-rich water up from the deep. Fishermen call these cold eddies or upwelling zones. They are ephemeral features, moving with the meander. A captain must track the specific curve of the river to find the fish. It is a dynamic geography. The best fishing spot is not a GPS coordinate, but a specific physical process of spinning water that moves 50 miles a day. The stream is a moving banquet, and the predators must constantly chase the tables as they slide north. The impact of the Gulf Stream on the weather of Iceland is the difference between a frozen wasteland and a habitable island. Although Iceland touches the Arctic Circle, its ports remain ice-free year-round. The Irmingar Current, a branch of the Gulf Stream, wraps around the island, bathing it in 40-degree water even in the dead of winter. This heat keeps the sea ice at bay. Without this branch of the stream, Iceland would be encased in ice like Greenland. The entire history of the Viking settlement and the modern nation depends on this tenuous filament of warmth. It is a heating duct that runs under the sea, keeping the edge of the habitable world pushed just a few hundred miles further north than the sun alone would allow. The phenomenon of MEDIs, Mediterranean eddies, sometimes interacts with the Gulf Stream system in the eastern Atlantic. These are lenses of warm, super salty water that flow out of the Mediterranean Sea through the Strait of Gibraltar and drift westward. They are deep, spinning underwater UFOs of salt water. Occasionally, they drift into the path of the Gulf Stream extension. The interaction injects a pulse of salt into the current. Saltiness increases density, which is crucial for the sinking of water in the north. These salty vortices act as salt pills for the circulation, helping to maintain the density balance that keeps the conveyor belt moving. The health of the Gulf Stream is thus connected to the evaporation in the Mediterranean, thousands of miles away. The aesthetic beauty of the Gulf Stream has been captured by modern satellite oceanography, revealing it to be a work of fluid art. Thermal images show the stream not as a smooth pipe, but as a chaotic, swirling tapestry of turbulence. It looks like cream stirred into coffee, with filaments, whirls, and spirals of orange, warm, and blue, cold, water, mixing in infinite complexity. This turbulence is mathematically chaotic. It cannot be predicted perfectly more than a few weeks in advance. It is a visual representation of entropy and energy flow. To look at a thermal map of the stream is to see the pulse of the planet visualized. As sentitantini. Chaotic, beautiful mess of heat trying to find its way to the cold. The deep waterfalls of the Denmark Strait are the final destination for much of the water carried north by the Gulf Stream system. As the water cools and sinks in the Nordic seas, it flows south along the bottom. It reaches the underwater ridge between Iceland and Greenland and plunges over the edge. This underwater waterfall drops 11,500 feet, more than 3 times the height of Angel Falls, the highest waterfall on land. It carries 175 million cubic feet of water per second. This plunging cold water is the engine that pulls the Gulf Stream north. The mighty river on the surface is being pulled by a silent, invisible waterfall hidden beneath the ice of the Arctic, a gravity-driven pump that keeps the surface warm. The concept of ocean memory refers to the ability of the deep ocean to store heat for centuries. The heat absorbed by the Gulf Stream today and transported to the deep ocean may not resurface for 500 years. The ocean remembers the temperature of the Little Ice Age and the medieval warm period in its deep layers. The Gulf Stream is the mechanism of this memory, burying the surface climate in the abyss. We are currently living with the oceanography of the past, and the heat we add today will be the problem of a civilization 5 centuries from now. The stream is a time machine, sending thermal messages to the future. The vulnerability of the Gulf Stream to freshwater input is the subject of intense scientific study known as the hosing experiment. Climate models show that if the Greenland ice sheet melts too fast, the influx of fresh water could form a cap on the North Atlantic. Fresh water is lighter than salt water. It refuses to sink. If the water doesn't sink, the pump stops. The Gulf Stream would slow down or shift south. This would paradoxically cause Europe to cool down while the rest of the world heats up. It is a climate switch that is protected by a salinity threshold. We are currently testing that threshold, pouring meltwater into the engine room of the current, waiting to see if the gears will grind to a halt. And finally, we watch as the Gulf Stream slowly dissolves into the North Atlantic drift, losing its identity in the vastness of the Northern Ocean. The distinct blue walls fade, the speed drops, and the heat is surrendered to the gales of the winter sky. The water molecules that began their journey in the bright sun of the Caribbean, that raced through the Florida Straits and carried turtles past the Carolinas, are now cold, gray, and heavy. They prepare for the long descent into the dark, sinking to the bottom of the world to begin the slow, cold journey back south as part of the deep conveyor. The river ends, not with a whimper, but with a deep breath, exhaling its warmth to the world before diving into the sleep of the abyss, to rise again in 1,000 years in a different ocean, under a different sun. As we let the current carry us into the twilight of the north, let the motion of the water soothe you. The ocean is a system of endless circulation, a heartbeat that is too slow to feel, but too powerful to stop. The river of blue water will keep flowing, carrying the heat and the life of the planet in its silent, salty veins. If you enjoyed this drift along the mighty Gulf Stream, I invite you to leave a like, subscribe to the channel, and share your thoughts in the comments below. It helps this little vessel of curiosity find its way to other sleepy travelers. But for now, let the warmth hold you. Let the current take you. You are safe. You are drifting. Good night.